Hey guys, welcome back to another chicken math video. Today we're going over 1.4, polynomial functions and rates of change.
Okay, guys, so these are the learning objectives, and practically it's just talking about polynomial functions, finding the leading coefficient and degree. We'll also be talking about local and absolute maximums and minimums, and points of inflection.
All right, so first we're going to talk about the components of polynomial functions. A polynomial function is a function in the following form. This thing is really confusing to look at first, so we've broken it down. Coefficients are a, and they have to be real numbers. And then our exponents that go with our variables are represented with n, n-1, n-2, and so on. And they have to be positive integers. And a sub n can not equal 0. Now, the degree is n, this value right here, and that basically just means that it's the highest power in which the variable is raised. So n-1, n-2, so on are all going to be smaller than n. Leading coefficient, a sub n, that's just the coefficient that goes with the variable with the degree. And then our leading term is this whole term right here, and it's also the one that includes degree. So keep in mind how a lot of these qualities are dictated by the degree. And then a sub 0 right here is our constant. It's just the number with no variable. And keep in mind that this form right here is in standard form, which means the terms, as you go from left to right, the degrees will decrease.
Okay, so if you're really confused about that polynomial function equation from the last slide, here it is again, except we're actually using numbers. Okay, so to find the degree, we just find the term with the highest exponent. So our degree is 8. There's a term here, 5x to the 8th, so that's our leading term. And the leading coefficient is a of n of the leading term. So in this case, it would just be 5.
All right, now we're going to talk about local or relative extrema. So that's basically the point on a function's graph where the function goes from increasing to decreasing. So that means the output values increase to decrease or decrease to increase. So it's just that point. Or they can also be at the endpoints of a polynomial with an inclusive domain. So that just means if our x values, our inputs are restricted, those endpoints can also be local or relative extrema. They mean the same thing. So this demonstrates that this function right here has 3 local extrema. The purple dot is a local maximum. So if we look right here, we can see that the graph goes from increasing output values, so it's increasing, to decreasing output values. So this point right here is a local maximum. Now, vice versa is our local minimums. So this black and red dot, it goes from decreasing to increasing, decreasing to increasing. Again, that's our output values that are changing. So a way to look at that is just looking at the tips of our graph. And the reason why this graph wouldn't have local extrema at the endpoints is because it's continuous. There's no restricted domain, so therefore there are no endpoints for it to count. Something else to keep in mind is when we're talking about local extrema, so maximum, minimum, both of these apply. And this also applies with global maximum and minimum. We'll talk about that later. Whether or not we use input or output values to describe this depends on the question. Now, the value itself, our minimum and maximum values, we're going to be using the outputs to describe these, which is kind of strange because I know for a lot of math, we tend to use input values, our x values. Unless it says otherwise, we're going to use our output values. So for instance, our local maximum is 0.1, which is right here. And our local minimums, negative 0.4, negative 2.4. So we're using our output values. Keep that in mind. Of course, this doesn't apply if it asks for our x values.
Now we will talk about local or absolute extrema, and this basically is an extension of relative or local extrema, but at a much larger scale, essentially encompassing the entire graph. Absolute maximums are the greatest output value of a function, and absolute minimums are the smallest output of a function. In precalculus, all global extrema can act as local extrema. Additionally, if a function has no endpoints or no restricted domain, then there will not be a global max or min. And this goes only for degrees that are odd. If the degree is even, then the function will definitely either have a global maximum or a global minimum. Now, here are two examples. As you can see, both of the examples are essentially variations of the classic x squared function. And if in the first example, you can see that it has a global minimum. And just from looking at it, you can see that the slope goes from negative to positive, and the concave up shape is telling you that there is a minimum here. As for the second example, you can see that there is a global maximum, and you can essentially apply your knowledge of the first one onto this one. Just simply, it is concave down. This is a third example. This is x to the sixth, which is an additional even degree polynomial. So you can see that it does have an absolute extrema here due to the fact that it has an even degree. And since we mostly use the output values to describe maximums or minimums of or any extrema at all, the output of this would be roughly negative 1.25, and you would put that down if a question asked you to find the, and since you can see that it is continuous, there are no endpoints, and thus there are no extrema at those endpoints. No global maxima. But global extremas can also be local extremas. In this case, you can see as this function here, the absolute value of x. There are two bounds here, inclusive, of course, where it is where these two values are both absolute maximums from this field of view. And even if asked for local extrema, these points would also count as global or absolute extrema as well.
Okay, so next we have points of inflection. So that's just when a function changes from concave up to concave down or vice versa. And we talked about this in 1.1. But the good thing about precalculus is you don't need to know how to calculate the point of inflection yourself. So there should just be a dot, or it should be really easy to tell. Okay, so here we have a cubic function. So at the black dot, the function changes from concave down to concave up. So that's our point of inflection. Here it's roughly at x equals negative 0.25.
All right, so now we're moving on to our examples. This is the first example where we're identifying the degree and leading coefficients of a polynomial function. Now, we're going to learn more about what this tells us about the function in later units, but right now we're just sticking to identifying. So, what is the degree of w of x? That's our function right here. And you guys can pause to answer these questions, but the degree of w of x would be 9, because it is the biggest exponent that our variable x is being raised to. Now, this might have tripped you up a bit because this is not in standard form, so our degrees do not decrease as we go along our function. Keep that in mind because sometimes they'll switch it up like this, but always look for the biggest exponent. So that would be 9. Now, what is the leading coefficient of w of x? So again, that's the coefficient that goes with our variable with the degree. So in this case, it would be 2. And a little bonus of what we kind of briefly talked about earlier. If this function has no domain restrictions, meaning no endpoints, will there be a global maximum or minimum present? And the answer would be no. because our degree, again, our highest exponent is odd. So that tells us there will be no global minimum or maximum if our domain was not restricted.
Okay, so here we have P of x. So what's the degree of P of x? That's just the highest exponent, which in this case is just 4. So now we're looking for the leading coefficient of P of x. The number in front of x to the 4th is negative 12. So that would be our leading coefficient. Now we have a bonus question. So if the function has no domain or restrictions, will there be a global maximum or minimum present? And the answer is yes, because the degree is even.
Okay, so this is our third example, and this time we're going to be identifying the extrema and points of inflection from the graph of a function. Keep in mind that all values in our examples are estimated, as always, so we're not calculating this in any way. We're just going to be eyeballing it from the graph. And obviously on tests and homework assignments, it'll be really easy to tell where our points are, so don't worry about that. All right. So identify the relative minimums. So that's just the points in which our output values go from decreasing to increasing. So if we look on this graph, we can see from this point to this point, it's decreasing, and then this point to this point, we're increasing. So that point in which it changes would be our relative minimum. And again, for extrema, we're going to be using our y values because it doesn't tell us to use our x values or anything else. So this would be at 0. Now relative maximums, we just repeat the process except vice versa. So where it's from increasing to decreasing. So right here, we can see our graph increases and then decreases. The output values become larger, then become smaller. So this point right here would be our relative maximum, which is about 0.3. Now absolute maximums. So that's the highest point of our graph. Now we can see that this graph does not have a restricted domain. There's no dots indicating endpoint. It's continuous. So there is no highest output value. So there is no absolute maximum. And the same thing goes for the absolute minimum, since it decreases continuously. Now we identify the locations of the points of inflection, so where the concavity changes. So we can use the little rhyme, concave down like a frown and concave up like a cup, like we talked in unit 1.1. This graph goes kind of down like a frown, which indicates it's concave down. As we go along this interval, our rate of change decreases. Then it goes up like a cup. Our rate of change increases as we go along this interval. So this middle part right here, indicated by a dot, is our point of inflection. It changes. So the location would be about, say negative 0.5 to 0.2.
Okay, guys, so now we're on to our last example. And just like the other slide, we'll be finding relative and absolute maximums and minimums. So the first question is asking us to identify the relative minimum. So that's just the endpoint with the lowest output value. So in this case, that would be about 0. Identify the relative maximum. So that's the endpoint with the highest output value, which in this case is 2. Now we're identifying the absolute maximums. So in this case, that's also 2 because that's the highest output value endpoint. Identify the absolute minimums. That's also just 0 because that's the lowest output value endpoint. And finally, we're trying to find the point of inflection. So that's when the concavity changes. However, this function does not change in concavity, so there is no point of inflection. So this is a case where our relative extrema are also our absolute extrema, because all relative, Because all absolute extrema are also relative extrema, but not vice versa.
Okay, so that's everything for Unit 1.4, Polynomial Functions and Rates of Change.
Thank you guys so much for watching. Please like and subscribe, and stay tuned for more AP Precalculus videos.
Bye!
Bye-bye.
Bye!